Okay, so good morning everybody. So we will continue our discussion on probabilistic machines. So the first thing that we will see today is a claim that we left in our last class. So we saw these two variations in the definition of BPP, right? We saw strong BPP and weak BPP, and we argued that basically they are the same class, they contain the same set of languages. Okay, so let us see why that claim is true. So in particular weak BPP is contained in strong BPP, right, because the other direction is trivial, it follows from the definition. So what I will do today to illustrate this proof is I won't consider a general polynomial Sn and Pn. Okay, I will just pick the constant, I mean some constant polynomial, but the essential idea will be illustrated in whatever we do. So let us get started. Okay, so before getting into this proof, let me talk a little bit about probability. So there is something known as Chernoff bound in probability, which bounds the tail of a distribution. Okay. So what do we mean by tail of a distribution? So I will just come to that. So let us see what Chernoff bound says. So suppose we have random variables. So let x1, x2 up to xk be independent and uniformly distributed random variables such that, so this condition is very important, such that probability that xi is equal to 1 is some constant p. Okay, so p is some fixed number, and probability that xi takes the value 0 is 1 minus p. Okay. So the important constraint on these random variables are they can take only two values. Okay. So they can be either 0 or 1, and each of those random variables they take 0 and 1 with the same probability. Yeah, any question? Okay. So that is the condition. So that is the condition that Chernoff bound, I mean under which whatever we will claim next will be true. Okay. And for all i's, the xi's take value 0 with probability 1 minus p. Okay. So you can think it of like coin tosses. Okay. So suppose you have a biased coin which gives you head with probability, let us say 0.4 and tails with probability 0.6. Okay. So if you make 10 tosses of this coin, well, at each step your probability of head is 0.4 and probability of tail is 0.6. Okay. And each of these tosses are independent events, and they are uniformly distributed. Okay. So that is one picture you can keep in mind. Okay. And so what is the expected value of an event xi? Right. So what does it come out to be? it comes out to be p, right, because it 1 times p plus 0 times 1 minus p. So, therefore, if I define x to be the sum of all these individual variables, what is the expected value of x? Kp, right, because expectation sums up. Okay, so let us call this also as mu. Okay, so expectation of x, I will just denote this quantity as mu. Okay. So, then what Chernoff bound says is that the probability that x is bounded away from mu, that is the expected value of what x is, okay, by an amount of equal to some delta times mu, is not more than 2 to the power 2 times e to the power minus delta square mu by 3. Okay. So, in other words, the more we deviate from mu, I mean the probability that we are deviating from mu becomes exponentially smaller. Okay. So, one way to look at this is you can think of this as, so we think of this as a graph. Okay. So, these random variables give us a bell shaped curve here, where on y axis we have that probability that x takes the value, okay, let me not use t here, yeah, so let me use something like L maybe, and probability that x takes the value L. Okay. And we have mu sitting somewhere over here. So, the more we deviate from mu, the probability of that keeps decreasing exponentially. So, that is what Chernoff's bound states. So, there are okay. So, this is what is called bounding the tail of a distribution. So, this is the distribution of the random variable x, and these are the two tails of it, okay, where it is trailing down, and I want to bound that. Okay, so what is the probability that the random variable takes this value, what is the probability that it takes this value, and things like that. And Chernoff bound, the good thing about Chernoff bound is it gives an exponential bound on that tail. Okay. So, there are other types of such bounds as well. I do not know if you have heard of it, like Markov's bound and Chebyshev's inequality. Okay. So, they also give a bound on the tail, but for example, in the case of Markov's inequality, it only gives a inverse linear bound on the tail of the distribution. Okay. And the reason for that is that it does not assume any property of the distribution. I mean, x can be any random variable, okay, and it gives an inverse linear. In the case of Chebyshev's inequality, it assumes that the standard deviation is given, and with that it gives a inverse quadratic bound. Okay. But this gives a much stronger bound. Anyway, so that is the no, yeah, in our case, yeah, because these values else are discrete values. So, yeah, but you can think it of as continuous also. I mean, yeah, in our case it is discrete the way we have defined this thing, but we can also define probability in a continuous manner, and we can have a continuous analog of this entire thing. But yeah, Okay, so that was the deviation from the theorem. So let us get back to it. Okay, so what we want to show is that weak BPP is contained in strong BPP. So let L be accepted by a probabilistic polynomial time somebody there. So L is accepted by a probabilistic polynomial time machine M such that for all x let us say that the probability that given a random string y M of x comma y accepts, or let me write it as M of x comma y is equal to 1, okay, means the same thing, is let us say greater than 2/5 and the probability that one second. Yeah, let's write it here. If x belongs to L and the probability that M of x comma y is equal to 1 is less than, let us say, 1/5 if x does not belong to L. Okay. So, in particular I am choosing my polynomial Sn to be 5 and also the polynomial Pn to be 5 in this case, okay, but it does not matter. So, suppose if you toss a coin 10 times, okay, what is the probability that you will have, let us say, only one head? I mean, what do you think? Or let us say you have 0 heads. So, you can imagine that it will be something very low, right?
Binomial distribution NCP.
Right. So, binomial distribution will give you, and similarly you can ask the question that what is the probability that you have only 1 head, 2 head, 3 head, 5 head and so on up to 10 head. Okay. So, now let us say I want to, so what is the expected number of heads that you get out of 10 coin tosses? That is 5, right. So, now if I want to ask the question that what is the probability that the number of heads is less than 3, okay. So, that is it is at a distance of 2 away from the expected value of the total number of heads, okay. So, that probability is basically given by Chernoff's bound, okay. So, Chernoff's bound says that, okay, so if I want to calculate the probability that the number of heads is less than 3 or maybe greater than 7 in this case, that is equal to 2 to the power 2 times e to the power minus whatever is that appropriate delta square times mu by 3, okay. So, it gives you a way of answering these questions, okay. So, instead of 10 maybe I am looking at 1,000,000 coin tosses and I ask that what is the probability that only 1/10 of those fractions are heads. So, this thing will answer that question for you.
This is dependent on this distribution curve.
So, the distribution curve comes from the fact that you are doing coin tosses.
This distribution curve comes from the coin tosses and this bound comes from this distribution.
Right, yeah.
If you plot NCK versus K, this kind of problem will not happen.
NCK versus K, it will be some kind of a exponential graph, all right, because NCK attains its maximum value again for n by 2, for k equals n by 2, and it is a exponential function. So, yeah, but no, but the one thing here is that it is only giving a an upper bound on the value that we have here, okay. It need not be exact, but still, yeah. So, yeah, if you plot a continuous curve, then it will have something of this shape in Ck against k. Okay, so we have this, and then what we want to show is for all polynomials Q, there exists a machine. So it has to be a polynomial time machine M prime such that I will just write it in short, such that for all x, okay, the probability that M prime makes an error is less than 2 to the power minus q of x. Okay. So, I mean I just shortened these statements by saying that the error probability of M prime is at most 2 to the power minus q of x. Okay. So, let us see how to design M prime. Okay. So, what M prime does is actually quite simple. Okay. So, it does so first it runs M on x for t equal to, so we will just leave this as blank for the time being, so many number of times. Okay. So, we will just think of this as t for the time being, and then if at least 3t by 10 of okay. Then if M accepts at least 3t by 10 times, then accept, else reject. So, let us understand this algorithm M prime. So, what it does is that given an input x, it just runs the machine M on this x for t number of times. Okay. So, at each time with a certain probability the machine M either accepts or rejects, and then finally, if M accepts at least 3t by 10 times out of these t many runs, then we accept, else we reject. Okay. So, the reason why we picked this number 3t by 10 is because it lies between 1/5 and 2/5. Okay. So, that is the logic behind it. So, now let us see that what is the probability that M prime makes an error. Okay. So, here is where we will use Chernoff's bound. Okay. So, before going into that, let us define something. So, let xi be the random variable which is equal to 1 if M prime gives the correct answer in the ith run, okay, and let us say it is equal to 0 otherwise. Okay. So, note that this is again a random variable which takes only 2 values, because at the ith run m prime. Okay, so when I am running m on x for the ith time, so m prime either gives the correct answer or it gives the wrong answer. M, okay. So in the ith run of m prime, yes, I will just say it as, if m gives the correct answer in the ith run of, yeah, I mean, so just don't know, so maybe I will just frame the sentence as, if we obtain the correct answer in the ith run of m. Okay. So that is when we fix this as 1 and otherwise 0. So what is the expected value of xi? So suppose we have a string which is in the language. Okay. What is the expected value of xi in that case? Greater than 2 by 5, right? And in the other case, when x does not belong to L? No, think about it. So if x does not belong to L, what is the probability that m x comma y rejects? It is greater than 4 by 5, right? So here the thing is that xi is equal to 1 if we obtain the correct answer. Okay. So if the string is in the language, it says accept, and if the string is not in the language, it says reject. Okay. So we can give an upper bound on E of xy as it is always greater than 2 by 5. Okay. So in one case it is greater than 2 by 5 and in the other case it is greater than 4 by 5, but this is anyway a lower bound. So therefore, if we consider the random variable x, which is again the sum of the variables xi, the expected value of x, okay, so again let me denote this by mu. So this is greater than or equal to, actually these are strict inequalities, I mean the way I defined them. So I just keep that thing preserved. So that is 2t by 5, right. So now we are in a position to apply Chernov's bound. So well, not quite, so let me get there. So then what is the probability that m prime gives a wrong answer? So when is m prime giving a wrong answer? Think for a while. So let us look at, take one case. So suppose we have a string which is in the language. Okay. So then m prime will accept if at least 3t by 10 times m accepts. Okay. Otherwise it rejects. Okay. So that means m prime is giving a wrong answer when x is less than 3t by 10, correct? Because if x is greater than 3t by 10, okay, I mean the way I define the x's, it will anyway give you the right answer. So this again, if I substitute t for mu, so this is the probability that x is smaller than what? Okay. This is by a simple substitution, because mu is greater than 2t by 5. So I just substituted mu instead of t. Okay. So which implies that the probability that x minus mu is greater than 1/4 of mu is whatever Chernoff's bound gives us. Okay. So, how are we getting this probability from this? So, if x is less than 3/4 of mu, what it means is that the difference between x and mu is at least 1/4 of mu, right. Okay. So, actually this probability is a slightly more higher, because this is true if x is less than 3/4 of mu, as well as if x is greater than 5/4 of mu. Okay. But anyway, it does not bother us, because we are only trying to give a upper bound. And now we can apply Chernoff's bound here. So, this is nothing but 2 times e raised to, what is our delta? So, we have 1/16 times, what is our mu? Mu is greater than 2t by 5. So, we have 2t by 5 times 1/3. Okay. And if you just work this out, this is less than 2 times, I am sorry, 2 to the power 1 minus, yeah, there should be a minus here, 1 minus t over 120. Okay. So, now we can go back and fix what is the t that we want. It is 120 time. So, we want the error to be bounded by q of x. So, it is 120 times.
Where does 1 come from?
Oh, it is because of this 2. I mean, I can just write, I mean, I can just change e to 2, okay, because e is anyway greater than 2, and that is the extra one. Okay. So, if I substitute this particular t over here, what we get is this is equal to 2 to the power minus q of x, right. So, suppose it belongs to the language, I get a wrong answer when I only have less than 3t by 10 accepting answers for n, and actually the same thing also happens if x does not belong to L. So, in that case I would okay. So, if x does not belong to L, yeah. So, yeah, that is true, but I am just saying that why is this probability the same as this event. So, the probability that m prime is giving a wrong answer. So, if x is in L, our random variable is less than 3t by 10, and if x does not belong to L, okay. So, what do we have here? So, yeah, by take,
We have already taken e of x by as 2 by 5.
exactly. So, yeah, so I mean basically the way this xi is defined, okay. So, see, xi is equal to 1 if we are obtaining the correct answer. In other words, if the machine, I mean if the string is not in the language, then xi will be equal to 1 only if this machine rejects for at least so many number of times, and that probability is again greater than 4/5 because of the way we have our machine m, and that anyway gives you a lower bound of 2t by 5 on the expected value of x.
It should reject for 70 by 10 times.
Yes, yeah, it is rejecting for 7t by 10 times, and for those 7t by 10 times you are getting a 1 here.
So the probability for x will be greater than 70 by 10 in that case.
Where? Here?
In the m dash gives the wrong answer if x is greater than 70 by 10.
No, 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 no.
But reject.
No, no, no. So, m dash is giving a wrong answer. So, it is accepting less than 3t by 10 number of times.
Yeah, it is for correct answer.
Correct.
It is for if x belongs to L.
Right.
If x does not belongs to L,
Right.
m has to reject at least 70 by 10 times.
Correct.
So the probability should be something x greater than 70 by 10.
No, 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 no. See how is xi defined? So, it is rejecting 70 by 10 times at least, right.
So it will be 1 for 70 by 10 times.
But for each of those reject you are getting a 1 here, right. So, the probability that you are getting a wrong answer which is accepting. So, what is the probability that you are getting a wrong answer? That is m prime accepts. So, that is now less than 3t by 10.
We are getting 1 in the case m rejects and if x does not belongs to 1 for xi. And it rejects at least 70 by 10 times. X value will be at least 70 by 10 because x is the summation of all xi.
Less than 70, but if x doesn't belong to L, for a language, for a case where it's not 70, x should be less than 70%.
No, so what you are saying, say that again,
I'm saying that if x does not belongs to L,
right?
and m rejects on the ith run, xi is 1,
Correct.
and m dash rejects only if m rejects at least 70 by 10 times.
M rejects if
70 by 10 times. According to the definition.
Not at least.
No, not at most.
At least 70 by
correct.
So the value of x will be at least 70 by 10 if m dash rejects and x does not belong to L.
At least 70 by 10, okay.
So for m dash to probability for m dash to give the wrong, the conditions will be x will be less than 70 by 10.
Right. Okay. So yeah. So maybe I should have I should replace this with a less than equal to, because in one case then it should be less than 3t by 10 and the other case 70 by 10. So anyway this is a smaller probability. I mean anyway this is a larger probability.
70 by 10 will be 3t by 10 is smaller than 70 by 10. So if you take x is less than 70 by 10.
Okay. But so if we take this less than 70 by 10, okay. Anyway, yeah. So anyway, it doesn't give a wrong answer. Only you have a different value of t. But let me just see the definition of m prime. So
How it says at least 70 by 10?
huh?
At most 70 by 10 in the rejecting. At least 70.
No. So if m accepts at least 3t by 10 times, then we accept. So if you are rejecting, it means that it is accepting less than 3t by 10 times, which is more than 70 by 10, as he correctly pointed out. So if it is rejecting more than 70 by 10 times, here the sum of these random variables is yeah. So here basically I have that x is less than 70 by 10 in that case. Okay. So yeah, so then we can appropriately change all these things. So what do we get? So we have 70 by 10 here, so that will give us, huh? No, there is something wrong here, because this does not make sense then, this does not make sense. No, so yeah, so in one case we have that the probability is less than 3t by 10, and in the other case it is less than 70 by 10. That no, both are equidistant from mu, right? 3t by 10 and 70 by 10.
4t by 10 is the new.
2t by 40 by 10.
2t by 10 is close.
Okay. Yeah, but no, so but that you are getting by Chernoff's bound, but how can you say that here? Anyway, so
When we are thinking for x does not belong to L, then you have mu is greater than 4t by 5.
Correct.
So if you apply that below,
Okay.
so you will here instead of x less than 3 by 4 mu, x less than 70 by 10 implies that x less than 7 by 8.
So let's see. So, okay, so in this case,
Maybe we should do a separate analysis when x does not come.
So, we can consider two variables for the two cases, if x belongs to x belongs to.
yeah, so till this point I think it's fine. So instead of writing this as m prime gives wrong answer, what so one case is that m prime rejects when x belongs to L. So that is the probability that we are bounding here actually. On the other side, we have to consider that m prime accept when x does not belong to L. Okay. So then we have mu as 40 by 5, okay, and we have x is less than 70 by 10. So therefore, this is x is less than 7 mu by 8, right. So then I think it will work out fine. And then finally the polynomial that you can take is the max of those two polynomials. So this will give you a polynomial q, and the other one is giving you some other polynomial q prime, and you can take the max of those two. Yeah. So I think that makes sense also. I mean, yeah, I kind of overlooked this, but yeah, thanks for pointing it out. Makes sense, because we should have different bound on the two different cases. Okay, so is that clear to everybody? So it's basically just running through the same sequence of analysis, but taking the value of mu appropriate. I think the other one will be slightly larger, but anyway, so let's not bother about that. Okay, so yeah, so what basically this shows is that it doesn't matter what is the error bound that we consider for BPP, okay, and in particular we can go as close to inverse polynomial. Okay, so the next result that we will see again regarding BPP is that BPP is contained in P by poly, okay, and this was shown by Adelman in 78. So this follows from a very simple counting argument. Okay. So suppose we have a language L in BPP, then by the definition of strong BPP, we can assume that x belongs to L, then the probability that m, okay, so let us say we have L in BPP via a probabilistic polynomial time machine M. The probability that M, just write this as let us say we have it as greater than 2 to the power one minus 2 to the power minus 2n, okay, and if x does not belong to L, then the probability that m accepts is less than 2 to the power minus 2n, okay. We are just fixing this q to be 2n. So now suppose that for a string x of length n, M uses a random string of m bits. Okay. So, what we essentially want to count is so let us define a random string as bad. So, is said to be bad, okay, if is said to be bad for some x in 0 1 to the power n if m on x comma r gives an incorrect answer. Okay. Okay. So, the number of strings that are bad for x. Okay. So, let us say we fix an x. So, how many strings are there that are bad for a fixed x? In other words, that will give you an incorrect answer. Okay. So, maybe I can just write this as probability over r and m of x comma r equals 1. Okay. Just to illustrate what we mean by r here. Okay. So, how many strings are bad for a fixed x? It is at most, I'm sorry, yeah, it is at most 2 to the power m. So, that is the total number of strings, and we have a 1 over 2 to the power 2n fraction of them that are bad from this probability. Okay. So, therefore, the number of strings that are bad for some x, okay. So, in other words, I am calling a string bad for some x if there is some x in 0 1 to the power n for which that string is giving an incorrect answer. So, how much is that? So, how many such strings do we have in 0 1 to the power n? 2 to the power n, right. So, we can just simply apply the union bound. So, we have 2 to the power n divided by 2 to the power 2n times 2 to the power n. Okay. So, these two cancels off. So, we have 2 to the power m by 2 to the power n strings that are bad for some x. So, therefore, the number of strings, so I am just taking the complement of this event now, that are not bad for all x in 0 1 to the power n is how much? So, I am just taking the complement of this set. So, that is greater than. So, the total number of such strings are 2 to the power n. So, it is 2 to the power m minus 2 to the power m by 2 to the power n, okay, which is 2 to the power m times 1 minus 1 over 2 to the power n. So, what does this tell us? That there exists a y in 0 1 to the power m that is not bad for all x in 0 1 to the power n. Okay. So, what was the definition of bad? So, we said that a string was bad if it gave an incorrect answer. So, what we have shown here is that there is some y which is actually good for all x's. Okay. So, then what we can do is, so to construct the circuit C of n, just hardwire the string y into C of n. Okay. So, for every n, just hardwire that appropriate y. So, you can just call this as y of n to emphasize that it is for that particular n into that circuit and go ahead with the polynomial time computation. So, again this only gives an existential result. It only shows that there exists a circuit family which can compute BPP. Okay. So, yeah, it is pretty straightforward, just bring some counting argument. Okay, so we will stop here today. And okay, so we will carry on more about these things on Wednesday.